So welcome to the pre-recording of lecture 43, the last lecture in this spring 2025 course, scheduled for the last day of April. So the purpose of this lecture is to give a final review, second review, fourth review in total for preparation of the final exam, which will take place on Wednesday, 7 May, a week from now. Okay, that's the main date, that time and date of the event. Now, the final exam will cover everything that we have covered in class. So the main source are the lecture slides and, of course, the textbook that we follow. For this review, I will focus on the topics on the second midterm exam, and I also have a review question prepared on binary space partitions. So the way this review is set up, I have 6 questions, and I've selected 6 pictures from the slides. So I tried to be original with respect to the second review. So in some sense, the second review also contains very interesting questions concerning the second part of the course. And also, of course, there is the second midterm exam. So the exam is open book, open notes, so you have access to all the slides. And the answers need to be into a Jupyter notebook. You can also take pictures from the drawings that you have made and upload them as well. Okay, let's start. So the first question is on trapezoidal maps. So here you see an example of a trapezoidal map. So we have a number of line segments, and these line segments define a partition of the plane. So the partition consists of the trapezoids that are defined by the endpoints of the segments and the vertical extensions. The vertical extensions from the segment just below, or the bounding box, to the segment above, or the bounding box. So here you see an example of such trapezoidal map, but it's kind of a special one because we have 4 points lying on top of each other, or alternatively, 4 endpoints have the same x coordinate. So this makes that this delta, the central trapezoid in this picture, has at its one side, it has the neighbors delta 1 to delta 5. So it has 5 neighbors and 1 neighbor at the other side. So in total it has 6 neighbors. So we have shown that in general position, what makes these trapezoidal maps also quite interesting is that any trapezoid can have at most 4 neighbors, 2 at the left, 2 at the right. So this makes this an interesting data structure also for navigational purposes. But if the subdivision is not in general position, so this is an example, then actually any trapezoid can have an arbitrary number of neighbors. And that is kind of unfortunate. So therefore, the first question, what would you do if you have endpoints where, or you have line segments where several of the endpoints have the same x coordinate? So they are lying on top of each other. So explain how to deal with such configuration, and also, is there an extra cost of dealing with such configuration? So the point is that in any trapezoidal map, a trapezoid has at most 4 neighbors, except if the points are not in general position. So in some sense, can we somehow do something? Yes, we can. And what we discussed is that, so this is the answer to the first question, we had a shear transformation. So all the points are replaced by x plus epsilon y. So that means that uh, the endpoints are all different from each other. So they all have different heights. So if you are adding a little bit of the height to all the x coordinates, then you end up with all different x coordinates. So here on the example, you see it. I did some tiny calculations, and also the endpoints at the previous slide. They had very uh, large disks to represent them. So I represent them a little bit more carefully. But now you would say, look, that trapezoid, that central trapezoid, has now actually only two neighbors, although you could say that you still see these delta 1 to delta 5, but you have the delta 1 and this very tall and skinny trapezoid just under the delta 1 and right next to the trapezoid delta. So this is a shear transformation. So in some sense, the first line of the answer is just already sufficient. Now, if you look at this, so this actually indeed, every trapezoid has now at most four neighbors. But how much does this now cost to work with this? Well, the point of such shear transformations is that when you construct your trapezoidal map, your subdivision, you have to decide which point lies to the left or to the right. And that is something that you do by comparing the x coordinates. Now, when you are comparing the coordinates after the shear transformation, you are taking into account the height. And you can see that if the x coordinates are the same, you take the leftmost, as the leftmost point, you take the lowest point. So, and that is just a comparison. So on the picture on the previous slide, I also wanted still to explain what shear transformations are. Um, I actually was a bit overkill. So you actually just go ahead with your algorithms for the trapezoidal map, but whenever you have the same x coordinate and you have to decide which point lies to the left of the other, you just compare the heights. So that's just an extra constant cost, just an if statement that you put in there. Now, you may now be concerned with the emergence of many tall and very skinny trapezoids, but observe that you indeed get more trapezoids, but actually the total number of new trapezoid doubles at most. So you could also see this with the example. So we actually are having these neighbors. We have many, we only have for every point for which we have the same x coordinate, we have one extra trapezoid. So in the extreme case where almost all endpoints would lie on top of each other, we would have twice as many trapezoids as otherwise. But again, asymptotically, this does not change the cost. Okay, so that's the first question. The second question concerns Voronoi diagrams. Here is a picture I took, a picture that didn't appear in the same manner on the second review. So this comes from one of the lectures. So we are running the beachline algorithm. So the beachline is what is at the lowest part closest to the sweep line, uh, the lower ends of these parabolas. Now, here we have a special situation where three parabolas intersect in the same point. And this intersection point, if that happens, it lies at the center of a circle, and that center must be a vertex of the Voronoi diagram. So we called this a side event. And during the lecture, we just plainly stated the last sentence. So if you have this circle event, then you have a vertex of the Voronoi diagram. Okay, prove this. So here is the setup now for this question. So I'm introducing this question with a picture. A harder way of running this lecture is just giving you the statement. So we have three sides, we have three parabolas relative to the directrix, which is the sweep line. Now, if these three parabolas, they intersect in a single point, then that single point is a vertex of the Voronoi diagram. Justify this statement. You could start drawing, and in some sense, you should. That's a good way of working. But actually, to solve this question, you should look back to the picture on the previous slide. And well, because we have studied the course, we actually know this picture. It's in our head. So then, to justify this, we are writing down what it means to have a parabola. So parabola is not algebraically y equals ax squared plus bx plus c. No, a parabola consists of all the points at the same distance from the focus and the directrix. Now, the focus of each parabola is the site, and the sweep line is the directrix. So what the three lines here essentially are saying, these three lines here that you see are expressing the fact that Q lies on the parabola which has as focus the side pi. Then the second line says that the Q lies on the parabola with focus pj, and the third equation states that the Q lies on the parabola with focus pk. So what it means is that being on the parabola means that the distance to the directrix is the same as to the focus. So that means that Q lies at the same distance of all the three sides. And that is what we defined as a vertex of a Voronoi diagram. A Voronoi diagram, by the way, is a partition of the plane in cells such that every cell contains the points closest to the site. And here, when you have three cells that are neighboring each other, they have one vertex in common. And that's here the property. Okay, two questions done. Let's go to arrangements of lines. So we introduced arrangements of lines with a problem from computer graphics related to the computation of the intensity of pixels, which we then solved by duality. So in passing, we defined the duality of a line. So here you see the dual of a line. So we have L has a slope m and intercept b. Then the dual of this line is the point where the first coordinate is the slope, and the second coordinate is minus the intercept of the original line. So we defined the dual of a line segment as the double wedge. So for any point on the line segment in the dual, we consider all the lines through the common point and where the slope ranges here on the example, the slope ranges between -1 and 1. Okay, so that was kind of a curiosity, an extension of the definition of what is the dual of a line segment. And then we didn't do anything with it. Well, that's kind of bad. Looks like in the course we did a lot of things that were actually not so useful. Now, suppose that you would like to, you are faced with a problem where you have to intersect wedges. So here is the setup. We have n tuples, where the first two elements are the coordinates of the point through which all the lines in the wedge are running. And then we have the slopes, alpha and beta. So we look at a wedge, a double wedge, where we have all the lines within a slope. So slope also within a range. Okay, so now we have this structure, so many wedges, so in our partition, so you can think of butterflies with very expanding wings. Do they all have a common point? And how would you solve this problem? So define solving in this course means that you define an algorithm. And how quickly can you make that decision? So whether there is a common point in all these wedges. Now this is on its own an interesting geometry problem, and you will certainly gain credit if you start your solution on your own. So you can start from scratch, but we just introduced duality. And by duality, we can reduce it to a problem that we have solved before. So what is the answer? Well, we've seen that the dual of a line segment is a double wedge. The dual of the dual is again the original. So if we are dualizing this problem, we have a set of line segments. And since this is the second review, we can solve this. So because we know this was something that we studied in the second chapter. So we have an algorithm, a good algorithm, to solve this problem. So for every double wedge, we have two lines. We take the duals of that, and that actually defines the endpoints of a line segment. So we have n line segments, and if we have line segments, what did we do with them? Well, we intersected them. So if we have a line segment, two line segments that intersect each other, that's a point. In the dual of this problem, well, if you take the dual of that line intersection point, the dual of a point is a line. So actually, if we go back to the original problem, is there a point in containing in that intersection? Is there actually a line which intersects all the line segments? I think the slides have it better. So the point is that we have dualized this. Every wedge corresponds to a line segment. If there is a line that intersects all those segments, then actually the dual of that is a point. And the dual of that line, that point, belongs to all the double wedges. So we solved the line segment intersection, but there is somehow a catch, and in some sense I had to think about this. So when we running the algorithm for the line segment intersection problem, we have a sweep line that comes down. Now, if that sweep line intersects all line segments, we talked about the status, then actually we know that the sweep line intersects it. So it suffices that at some stage in the algorithm, the sweep line intersects all line segments. But you can think about it, so you can imagine configurations where a horizontal sweep line is going to miss line segments. And by just tilting the sweep line, you will actually find intersections. So what you do is you run a rotational sweep centered at the middle of all the endpoints. So you can, so in some sense, we start thinking again about wedges. The wedges are now defined by this rotational sweep line in the middle, and it sweeps actually over the segments. So actually, two segments define a trapezoid. So we've worked about trapezoids. So, and the center of the trapezoid, if you take that as the center of your rotational sweep, then you can see that the center lies in the convex hull of this trapezoid. So you can find a line where you actually enter and leave the trapezoid through the line segments. So that's kind of the motivation for the rotational sweep. Okay, the cost of this algorithm. So we've seen that this line segment intersection was actually our first algorithm that was output sensitive. But here we actually don't care too much about these line intersection points. We don't care where the line segments intersect each other. We only care that the status at some point contains all line segments. And then we can stop. Um, so we are running this algorithm and we have to sort all the points in their polar coordinates. So the sorting happens at the very beginning. So this defines the event queue. So we're going to move our rotational sweep line based on the angles sorted. So, and if we see that in every step we are having more and more segments, then actually we know that there is a line that intersects all the line segments. So we may have to process all the points, that will take n steps, but n log n is the time. So we can solve this decision problem and also actually find the line and the point that lies in all the double wedges in time n log n. If you don't know duality, it occurred in other instances, then you may come up with also an algorithm that works, but it should also rely on sorting in some way or another. So this n log n bound will most likely also show up. Okay, three problems solved. We are in the middle, and also the middle of this recording. So Delaunay triangulations. Delaunay triangulations optimized the smallest angle. So it's a triangulation of a point set. And we gave the characterization of the optimality via a circle. So Delaunay triangulations are dual to Voronoi diagrams, so it's actually not a coincidence that we see circles again. So here is the theorem that we relied on. A triangulation of a point set is Delaunay if actually all the triangles, if you take all the circles around them, they do not contain a point of the point set in the interior of that circle. So you see the construction. So we declared that edges inside the triangulation were illegal if you have a situation that is represented here. So we have the triangle RPQ, and if so, triangle defines uniquely one circle, And if you have a point S is another point of the set capital P, of which you want to construct a triangulation. If we have this other point S inside the circle, then this triangulation cannot be Delaunay. Okay, here is then the question. So the question was phrased with that picture in mind. We have 4 points. The 4 points are defining a quadrilateral. So you could look at these points in the clockwise sense. R, P, S, Q. They actually rely on a circle, if you like. We have the edge PQ, and the decision on whether the edge is legal or not, or illegal or not, um, is actually, there might be a borderline case. So when is that decision actually, is that decision might be critical, but does it, is it, how sensitive is this? So what happens to the criterion if you have to make this decision at the border? So what actually does it actually mean, borderline? Okay, when you look at this question, always the first instinct is to try to visualize, try to think geometrically, and try to relate to pictures that we have seen in the lectures. It might also be good always to flip through the textbook. Textbook has also a lot of pictures, and see which page corresponds to what you have in your mind. So here is the borderline situation. So we had the RPSQ, the points that were lined up in counterclockwise way, and they define a quadrilateral. So in one situation we have the edge PQ, and in the other situation we have flipped that edge, exchanged it for the RS. And we keep in mind the theorem. So the theorem states that if for any triangle there is a point inside the circle, then it's an illegal edge. But here you see that we have two circles. Actually, it's the same circle, but all the 4 points lie on the same circle. Does it actually matter now when we start to decide? Well, what do we look at? We look at the size of the angles. We applied the circle theorem of Thales for that. But you can look at, so here suppose that only the quadrilateral matters. So there are still, of course, many other sides, many other points involved in this capital P set. But here what we are comparing are angles. So if you have a hard time because the accuracy of the points is not high enough, or it is high enough but your arithmetic is somehow subject to round off, then you can see that if you have hard time comparing which angles are smaller than the other, or they are very close to each other, then actually it doesn't matter, because also for the picture the resolution is such that we can't really distinguish which configuration has the smallest angle. So another way of saying both are valid edges. You cannot pick both at the same time. So this would be a very uncomfortable, a wrong case. You would not have if you have both the edges PQ or RS. But if your algorithm flips a coin, somehow has a canonical way of deciding, then it will always come up with the same triangulation. However, the Delaunay triangulation, in some sense, it does not exist, so there are multiple Delaunay triangulations. That is also something to be aware of. Okay, windowing queries is our next to last problem. So I just copied this slide verbatim. So back to the windowing problem. Uh, how did we come up with a solution of this problem? Well, what we did is we had a number of line segments, and what you see here on this slide are the segments. So we have small segments, we can have several of those, and we have large segments that contain many elementary intervals. So the way we considered those segments, we constructed, we looked at the x coordinates of the endpoints and we sorted them. And that defined a sequence of elementary intervals. So if we need to locate a point, we can apply binary search to first look at the x coordinate and decide in which slab we are. And then also the segments in the slab are ordered. So also here we can apply a binary search. It's a primitive operation to decide whether a point lies above or below a line segment. So when you do binary search, you pick the middle segments in your slab and you are um, sorting it. So we have and you are locating it. So I'm sorry. So you are going to the top half or the bottom half. So that's binary search. So what we have our segment tree. This is what you see with the slabs. And then we have the associated structure. So we have what is above and what is below. So we have the node that consists of S1, and then we have the segments that are above and below in the nodes V2 and V3. Okay, that's the background. We want to do window inquiries. So we have a window, qx prime is the range for the x coordinates. Qy prime is the range for the y coordinates. We are given the segment tree that stores the n line segments, and we have the associated binary search tree. Now, what is the cost to find all segments in the W? And also explain the search algorithm. I explained the search for locating one point. Here actually we need to find the line segments within a range. So we have to report all the elementary intervals, all these segments. Okay, how do you do this? Well, I explained how to do the vertical query. And I'm applying actually a theorem. So the theorem states that if you do two binary searches, so the vertical queries are actually, if you do this also for the y coordinates, it's going to be quadratic in the logarithm of the total number of line segments, and it also is proportional to the number of reported segments. So I'm copying from a statement of the theorem. So I did not state the theorem on the slide that was prior, but that is a result that we are using here. Now so this theorem was on vertical queries, where you don't have a range, but actually you do have only one x, so you don't have an interval. So you have to do also a query on the not only on one bound, but you have to do many of them. Now, it's important here that the problem is discretized, so we actually are knowing how many segments we have in advance. We actually know the number of slabs that we had. So in the segment 3, we started with the leaves that were all the elementary intervals. So there are, say, L slabs in between. Then actually we have to use that many vertical queries. And I'm actually multiplying the cost for one query times the number of intermediate slabs that we have to investigate. Or actually the total number of slabs, if you like. The big K is the sum of all the output that you get, or actually the total output. So you get a bound that is proportional to the square of the logarithm of the total number of line segments. Okay, so that was the next to last problem. Now I have one problem left. I also have time left, but this is the last lecture, so we're going to end earlier. So I pick one topic from the end, and that's binary space partitions. So this comes again from computer graphics application, where you have to decide the visibility of objects. So one way to do this is by partitioning the objects. And here the objects are triangles. So you could see this as a projection of a three-dimensional object in the plane. Or you could also, from here on, imagine the generalization to three dimensions, where every triangle represents a facet of a convex hull or of a triangulation of a surface. So the binary space partition is defined by a sequence of lines. So you see the I. So we are first, we are applying essentially the painter's algorithm. We first rendering the objects that are farthest away. So this is kind of painting the background. Then we are painting everything that is inside that line, which we can't see, by the way. And then we paint everything over that. So over the background, we paint the elements that are closest to us. So this is how this binary space partition is used. So this is this was one of the slides of this chapter on binary space partitions. Now, it turned out that we had to fragment our objects because otherwise we couldn't really decide on a unique ordering. So some triangles might be overlapping other triangles that then overlap other triangles, and these other triangles overlap the original triangle. So fragmentation was necessary. So we start with n objects. And the concern is actually if we do this fragmentation, so you could actually also have seen this on the slide, I should have pointed this out, that if you cut a triangle with a line, you have several pieces and you have to triangulate those trapezoids again. So you can cut a corner from a triangle and that corner could be a triangle, but what remains is a trapezoid. And then you have to triangulate that again. Okay, what is the growth of the number of fragments? How come this algorithm really works? How come it is efficient? So if the number of fragments grows exponentially, then it would not be an algorithm. We would not have covered it in this course. So the question is that how many fragments can we actually have in general? Well, there is the auto partition. Also, we may assume that all the triangles are in general position. So when we are intersecting a set of triangles with a line, it's not that we will hit all the triangles and then fragment all of them. No, we will apply auto partition. We will actually have lines that pass through an edge of a triangle. And that actually will fragment not that triangle. And if we have to split, then again, we can take just yet another edge of that triangle. So in some sense, every triangle generates their two splitting lines. And what we also observe, and you could see this also on that picture that I showed introducing binary space partitions, is that many of the lines are actually only half lines. So there's actually only one line in general that runs through the entire plane. Many splits will actually defined by line segments, and some of them are half lines. So that means that drastically reduces the fragments. So another way, you could also see that this binary space partition defines a tree. So you have all the triangles in the left, all the triangles in the right, or below and above, or at one side of the line and the other side of the line. And you may expect that this is a very nice balanced tree. Each time we cut the remaining number of triangles in half. So we end up with something that is of size expected to be n log n. Now this is an expectation with a lot of assumptions. Um, and in some sense, it is an optimistic bound. It's at the end of the review, also at the end of the course. Um, in a section that we didn't cover, it is proven that n square is actually what also covers the worst case. So the book says that it's not in general proven that this is n log n, but that is mostly expected. That if the objects that you are rendering are sufficiently general, random, then you will have a very nice balanced binary space tree and with very little fragmentation. Okay, I hope that this review was interesting. It might also be a way to look at the course backwards. So if these problems are interesting, uh, especially for the subjects at the end, uh, look back at the slides, look back at the textbook.